Students, welcome to my YouTube channel. In this video lecture, I am going to answer questions from sample paper number 3, 4th edition RK Bali book. So let's start with question number 81. Which of the following equipments uses primary radar principles? GPS, airborne weather radar, secondary surveillance radar. Now, out of these three options, option A is wrong because GPS uses satellites for its operation and not a radar. Okay, airborne weather radar and secondary surveillance radar, both of them do make use of radar. Now, out of these two, airborne weather radar uses primary radar, and the secondary surveillance radar uses secondary radar, as is obvious in its name. Okay, so primary radar. What is primary radar? Now, let's say this is your ground. This is your primary radar on the ground. There is aircraft in the atmosphere. Okay, aircraft in the atmosphere. So what will happen? This primary radar will transmit radio pulses in the direction of this aircraft. Let's say at a frequency f. This radio pulses will strike this aircraft and return to this radar on the ground at the same frequency f. That means a primary radar uses one frequency throughout its operation. One frequency for so the transmitting frequency equals to receiving or reception frequency. In case of secondary radar, let's say this is your radar on the ground. Again, you have aircraft in the atmosphere. What will happen? This aircraft will transmit radio pulses in the direction of this radar on the ground. Okay, in this case, let's say your aircraft is the interrogator. For example, distance measuring equipment. It's a form of secondary radar in that the transponder in your aircraft sends an interrogating signal or interrogation signal towards this ground station, which will be called a transponder because it is going to respond to this interrogation signal. So transponder, right? So it sends this interrogator in your aircraft, sends interrogating signal towards this transponder. This interrogating signal is at 1090 megahertz. Transponder will reply to this interrogation pulses by sending reply pulses in the direction of aircraft. By sending reply pulses in the direction of this aircraft at a frequency of 1030 megahertz. So you can see here there is one frequency for interrogation signal, a separate different frequency for reception or reply signal. So in secondary radar we use two different frequencies, one for interrogation, another one for reply. In case of primary radar we use the same frequency for interrogation as well as for reception. So that is the difference between them. So airborne weather radar is a form of primary radar. Okay. Secondary surveillance radar is a form of secondary radar. So option Bravo is the correct answer. Do watch my lectures in which I have solved all the airborne weather radar questions from Keith Williams, RK Bali, Oxford. I have also marked important points from airborne weather radar chapter in Oxford Radio Navigation textbook and uploaded that video lecture to my channel. So you can watch that lecture, make notes of important points, mark the important points in your textbook, and you can only revise those important points again and again for your exam. Next, what is the wavelength of high frequency? So the wavelength of high frequency, frequency band of high frequency is 3 to 30 megahertz. 3 to 30 megahertz. And the frequency for high frequency will be in terms of meters, that is 100 to 10 meters. 100 to 10 meters. The corresponding wavelength of high frequency will be 100 100 to 10 meter. Remember this. Next. The least attenuation of a sky wave is likely to happen at midnight and high frequency, midday and high frequency, midnight and low frequency. So the correct answer here is option Charlie. Least attenuation happens. So as frequency increases, attenuation increases. As frequency decreases or reduces, your attenuation will reduce. So attenuation is least likely to occur with a low frequency and midnight. So option Charlie is the correct answer. Diffraction of radio waves. Diffraction is nothing but bending of radio waves. Increases with increasing frequency, decreases with increasing frequency, is constant at all frequencies. Let's say this is your Earth surface. Here is the transmitter. Okay. Consider this your ionosphere layer. This is your ionosphere layer. Now when this transmitter transmits a radio signal in the direction of ionosphere, at a particular angle called critical angle, that radio signal will bend away from the ionosphere and reach the Earth's surface, and it will reach the Earth's surface. Now, as you keep increasing the frequency of the signal, this bending from the ionosphere will start reducing. At one point of time, at one particular frequency, this bending will stop, and the entire this complete radio signal will pass through the ionosphere out into the space. Okay, but as frequency increases, this bending stops. As frequency decreases, goes on decreasing, the bending will happen and the signal will return to the Earth. The more you decrease the frequency, the more you go towards low frequency band, medium frequency band, very low frequency band, this sky wave will no longer occur. What you will get is, you will get a surface wave. Okay, so you will have to strike a balance between very high frequency and very low frequency. Your frequency should be somewhere between medium frequency band and high frequency band. That is where you are bound to get sky waves. Okay, beyond high frequency band, that is VHF band and above, you will get space waves. Space waves are nothing but waves that directly go out from the atmosphere of the Earth into the space. Okay, so as you increase the frequency, diffraction of radio waves will decrease. This bending away from the ionosphere will decrease with increasing frequency, because as you go on, as you keep going on, as you keep increasing the frequency, the sky waves will transform into space waves, line of sight waves that we say. Okay, and they will go away from the atmosphere into the space. So very important point. Sky waves at day or night are least likely with what? So like I said just now, very high frequency. So sky waves are primarily found in high frequency band. Okay, are primarily found in high frequency band. Okay, they are the primary means of propagation in the HF band, that is high frequency band, and they can also be used in the medium frequency band. Okay, after that you have to remember, in case of low frequency, okay, in case of low frequency, you do get sky waves, but the main or the primary mode of propagation is surface wave. Okay, surface wave. So the main odd one out here is very high frequency. You will not get sky waves in the very high frequency band, in starting from very high frequency band, ultra high frequency band, super high frequency band, so on and so forth. So option A is where you are least likely to find sky waves. The optimum high frequency puts the receiver just inside the minimum skip distance, just outside the minimum skip distance, just within the surface wave coverage area. Now just now I drew this diagram of sky waves. So this is the transmitter, this is the ionosphere, this is the returning wave. So I'm going to label this. This is the first returning sky wave. First returning sky wave. Now, The distance from the transmitter to the place where the first sky wave is received successfully is called, that is called skip distance. That is called skip distance. Okay. Now, here they have asked us the question. Now, like I said, in the high frequency band, you are most likely to find sky waves. So, this particular question, the optimum high frequency means the best suited high frequency puts the receiver. Okay, transmitter will transmit the radio signal towards the ionosphere. It will get refracted and come back to the earth. The distance between the transmitter and the first wave that is returning to the earth is called skip distance. So this optimum, when you make use of this optimum high frequency, this best suitable high frequency for your operation, it will put the receiver, maybe your aircraft, let's say, just outside the minimum skip distance. Meaning, when you use this optimum high frequency signal, your aircraft receiver, the airborne receiver equipment in your aircraft, will be able to process or receive this returning skywave successfully. If your aircraft, in order to receive the signal and forthcoming skywave signals, your aircraft must be beyond the skip distance. Okay, somewhere here, beyond this skip distance. If your aircraft receiver is within the skip distance, somewhere here, okay, inside the skip distance, you will not be able to intercept or receive that skywave successfully. The aircraft must be out of that skip distance, and it is possible when you are using the correct high frequency that will enable the signal to go to the ionosphere, get refracted, and come back to the earth. Okay, so that's why the answer to this question will be just outside the minimum skip distance. Next, surface wave range decreases with increasing frequency, is independent of frequency, decreases with decreasing frequency. So correct answer is option A. Surface waves. Surface waves are nothing but the waves that follow the curvature of the earth. Now as frequency of a radio signal increases, attenuation also increases. Attenuation is nothing but loss of power, right? So the wave, so as you increase the frequency of the signal, attenuation or the loss of power will increase. As a result, the signal will not be able to travel far off distances, will be able to travel long distances, because attenuation is happening, absorption of signal power is happening. Okay, so as you go on increasing the frequency of the radio signal, the signal suffers from attenuation, and this prevents it from achieving very long ranges. So surface wave range decreases with increasing frequency. Option A. Atmosphere ducting close to the earth is most likely in an inversion with constant humidity, in an inversion with humidity decreasing with altitude over the land surface. Now what is atmospheric ducting? Let's say this is your earth surface. If there is an inversion above this earth surface, what is an inversion? Inversion is that phenomenon in which there is tendency for the temperature to rise with increasing altitude. Now, what is a standard expectation? That as you go to higher and higher altitudes, atmospheric temperature decreases at a lapse rate of 2 degrees Celsius per 1000 feet. But in case of inversion, there is a unique display that we get to see. The atmospheric temperature increases with increase in height. So let's say this is an inversion layer. You are getting an inversion layer on this particular day. So whenever there is inversion in the atmosphere, the radio waves that are sent by a transmitter, this radio waves will suffer continuous bending towards the earth, then again they will be pushed upwards, then again they will bend towards the earth, and this will keep happening repeatedly. Okay, this will keep happening repeatedly, and it's nothing but a blessing in disguise. The side effect of this, or the net result, is that the signal travels much larger distances, much beyond expectations. Okay, so this is called ducting. This phenomenon is called ducting, and this question was asked. They asked me this question in my ATPL YY exam. What is ducting? What happens with ducting? What is the result of a ducting? Okay, so ducting is nothing but a phenomenon in which radio signals bends towards the Earth's surface, and the result is that we get much longer distances with this phenomenon. And the favorable conditions for ducting are: first, inversion layer; the second, humidity must decrease with increase in altitude. Humidity must decrease with increase in altitude. So atmospheric ducting close to the earth is most likely to happen in an inversion with humidity decreasing with increasing altitude. To mark some important points from this paragraph, super refraction is nothing but ducting. So here they have written the conditions favorable for super refraction or ducting: decrease in relative humidity with height, temperature falling slowly with height than standard. Okay, that's why we are getting inversion. Fine weather, high pressure systems, that means stable atmosphere, warm air flowing over cool surfaces at the time of night. So in extreme cases, when there is a low temperature inversion with a marked decrease in humidity with increasing height, simply warm dry air above cool moist air. A low level duct may be formed which traps radio waves at frequencies above 30 MHz, that is above high frequency band, giving extremely long distances. This phenomenon is called duct propagation and can lead to exceptionally long ranges. So underline this paragraph, you must remember this, the favorable conditions and what are the advantages of this phenomenon. Okay, next point. Very important next. The BFO in an ADF. BFO is nothing but beat frequency oscillator. ADF is your automatic direction finding equipment. It's an airborne equipment. The corresponding ground equipment is NDB, non-directional beacon. Now what happens? Your ADF operates in the frequency band of some 190 to 1750 kilohertz. Now whenever you tune into an NDB station, you want to hear the identification, you should be able to hear an audio signal. Now, what commonly happens is that the frequency range or the frequency band in which ADF operates, it doesn't enable us to hear an audio tone signal. So to enable us to hear the audio tone signal when we are tuning into a station, trying to identify that station, we make use of a beat frequency oscillator. This beat frequency oscillator uh, produces, okay, or superimposes an audio tone on the main carrier wave. So, in addition to the carrier wave signal, so we have a normal main ADF signal. The beat frequency oscillator will superimpose, or in simple words, it will produce an additional audio signal, especially for us to be able to hear that identification code of the NDB ground station. That is the job of beat frequency oscillator. It produces an audio frequency which is approximately 1000 hertz different from the main carrier frequency. Okay, so the BFO in an ADF produces a signal that differs from the received or the main signal by approximately 2 kilohertz. That's fine. Produces a accurate 2 kilohertz signal, minimize static interference. So option A, approximately 2 kilohertz. Some books it's written 2000 hertz. Uh, in other books it's 1000 hertz, so approximately that much. But the main job, they can ask you in this SPL Viva or ATPL Viva, what is the main job with beat frequency oscillator? So the main job of it is that to enable us to hear the identification of the NDB signal, because the main carrier wave of the ADF does not enable us to hear the identification signal. So the beat frequency oscillator produces a new audio tone in addition to the main carrier wave that we already have. Okay, and this audio tone is useful for tuning and identification. Question number 90. For a VR and DME beacon to be said to be associated, the aerials must not exceed dash in a terminal area. So I have covered this question many times, especially in the DME lectures that I have done. You will find many DME lectures in which I have solved back questions from Oxford Radio Nav DME chapter, Pete Williams, RK Bali, and there is another book called Ground Studies for Pilots by RB Underdown. So I've also solved questions from that book. So do watch all the DME lectures, very nice and very important topic. So in that I have said this many times. A VR and DME stage aerials can be regarded as co-located, okay, or associated when the location of the aerials are not separated by more than 30 meters or 100 feet in a terminal area. Outside terminal area, the threshold is 600 meter or 2000 feet. Okay, so you must know this by heart over here. So there are three conditions under which your VOR and DME can be considered co-located or associated. When first, both transmitters are co-located at this exact same location. The maximum distance between the aerials is 30 meter maximum. 30 meter translates into 100 feet, okay, in terminal area. Outside terminal area, the maximum space between them must not exceed 2000 feet, equal to 600 meters. Okay, so in these three scenarios, the frequencies will be paired. So whenever you tune into a VOR frequency, automatically DME station will get activated. Identification. How do you identify between VOR station and a DME station? Now both will transmit the same call sign depending on the location. Okay, there are four identifications. Out of those four identifications, the first three belong to the VOR every 30 seconds, and the last 10 seconds you will hear the identification of the DME station. Okay, so the DME transmits the fourth ident, the VOR transmits the first three idents for the first 30 seconds, and the last 10 seconds, the 40th second, you will hear the DME ident. Now they won't be regarded as associated, uh, so if they do not follow any of these three criteria. Okay, so in that case they won't be associated, they won't be regarded as associated. But if still they serve the same location, the frequencies will be paired, and in that case identification, first two letter of the identification are the same, VOR as well as DME, but the last letter for DME identification will be Zulu, Z. Okay, if they are not associated but serve the same location. And if they are widely separated, like hugely separated more than 6 nautical miles, the frequencies may be paired or may not be paired, and in that case the identifications for both DME and VOR will be totally different from each other. So very important table, remember this. With this question, we come to the end of this lecture. I hope you have understood these 10 questions. These 10 questions were mainly theoretical, so a proper understanding of theoretical chapter, memorization of facts, rules, criteria is very important. So do watch my lectures in which I have marked important points from DME chapter, okay, radar chapters, VOR, ADF chapters. I have also solved questions of ADF, VOR, track and drift questions from RK Bali, Keith Williams, and Oxford as well. So do watch those video lectures. When you watch that video lectures, you will come to know how to solve those numericals, and also at the same time your concepts will get revised and better, because while solving the numericals I have also explained the theoretical concept behind every logical solution. So that will be a very good revision for you. Best of luck. In my next video lecture, I will solve the next remaining questions. So I'll see you there.